right, welcome back everyone. So now we're talking about something that we have completely ignored so far, which is shadows, because shadows are very important in graphics, of course. For example, I have here an image that I copied from the chapter about visual perception, and we see here that at the top and at the bottom this is the very same image. The only difference is where we place the shadow in our image of these spheres here, and you see that it of course creates a completely different impression and a completely different perception of the image based on how we place the shadows there. But more importantly, of course, shadows are part of what we see in real life, and if we model a scene and do all the light calculations perfectly, but then you see that there is no shadow in the scene, it just doesn't look realistic. So we have to do something about the shadows if we want to model a realistic scene. Unfortunately, doing that isn't easy, and shadows are not part of the standard pipelining graphics, but there are of course a couple of approaches to deal with this, and this is what we're going to talk about now. So first, the distinction, or a little bit about shadows in general. I already said we make in graphics the distinctions between so-called hard shadows and soft shadows. The hard shadows are shadows which have a hard line, where we have a hard transition between shadow and no shadow. Whereas for a soft shadow we have a smoother transition between the area that is completely in shadow, has a complete shadow, and the area where there is no shadow at all. And technically, or the terms for this is, we call the region where we have a complete shadow, where there is no light at all, the umbra, and the area that is partly between the light and partly between the shadows, the penumbra. And this is of course intuitively, or it's clear why we have this in reality. We have these smooth transitions here because we usually don't have in reality a light that is just a single spot that shines, but we have a light that goes a little a wider range. And then of course you see here that you have, if this is an object that causes the shadow, which we usually call the occluder, then, and the area that hits, where the light hits it, where we have then the shadow, is called the receiver. And then you see here, of course, that you have an area here where no light, where the occluder occludes all light from that light source. But then we have an area here where the occluder doesn't occlude any light at all. But also we have an intermediate area where some of the light comes in and some of the light doesn't. And of course this amount of light that comes in or that hits the receiver here increases the more we move away from the occluder, which is why we have this smooth transition and not the hard transition that we have with the hard shadows. But of course it should also be clear intuitively that calculating the smooth transitions, calculating the soft shadows is much harder than calculating the hard transitions, or more difficult and also less efficient, which is why we will only address methods for calculating hard shadows. And the first one is something that I hope that some of you, for some of you this already sounds familiar, because this is also in the practicals. I think it's the first medium assignment, if I remember correctly. And this approach is called shadow maps, which are very popular because they are hardware supported, which also means usually they are relatively fast. And the idea of that is that we create a shadow map, that's where the name comes from, by placing a camera at the light source and then use a depth buffer from the light source to calculate the shadow conditions. And the idea behind this is like, if you think about the depth buffer or a set buffer that we used so far, the reason for using it was that we said if an object is behind another object, we cannot see it, so we only have to draw, or we only should draw, the object that is in the very front of us if we exclude transparency. And that's why we stored the set value of the closest object. Now if you look at a scene from a light source, then of course the first object that you see from that light source is of course the object that gets the full light. And if it is not a transparent but a closed object, then all the objects behind it don't get direct light, which means they have only the reflected light, which means they are in the shadow. So by knowing which is the closest object to the light source, we can also say which objects do have a shadow, and where we have to draw, on which objects we have to draw a shadow. And this is why we, in this approach, we put a second light source, a second camera on the light source. So let's call it EL, and this is our original camera, our viewpoint E. And then we fill a set buffer in a similar way as we fill it here with the coordinates or the set coordinate of the closest object. And then we compare those two set buffers with each other by transforming this set buffer into the coordinate system of the light source. So we have here a light, or let's call it E dash, and this is a light source E, a camera position E, and here a camera position E dash, which is at the light source. And that means here we get the set value, set L. I'm really screwing it up with the notation here. I should be a little more careful here. So let's call this also the light source L. Then we have a set value set L here, and we have a set value E set here, which is the first object that we see here. Now if we calculate that, then we get the set value of the object E set here, and then we compare it with that set value here. If this is the same here, then we know that this is not only the first object that we see from that position, but we also know that this is the first object that we would see from that position, which means this is the object that gets all the light. If the set value is smaller than this one, it means it is further away from the light source than another object, which means it's behind it, which means it is in the shadow. So by comparing these two set values, we can say if these depending on how they relate to each other, we know if we have to draw this in a shadow or not. And we get this by just multiplying it with a transformation matrix that transforms our coordinate system here to the coordinate system of the light source, which is a simple coordinate system transformation, which we can do with matrix multiplication like we learned before when we did the perspective transformation. So this is a simple transformation, and then we have this set value E set E, then becomes the value set E dash. And that's why I wanted to have this different notation here, because then we compare this E dash with this set value. No, we compare the set L with the set E. That is not the set E. What am I doing here? We do the transformation, and that corresponds then to set E dash in this coordinate system, and then we compare these two. If they are identical, we know the set values, we know it's the same object, which is the one that gets the light. If this set value is larger, then we know it is in the shadow. If it is smaller, that cannot happen, because that would mean it is smaller cannot happen because it would be closer then. So you have to be careful. I'm sometimes a little sloppy here in defining. If we look in the negative set direction, then of course it's not larger, it's smaller, but you get the basic idea here. Good. All right. Yeah. So this is the shadow maps, and I hope that I see some very interesting and impressive implementations of it once you're done with the third practical assignment. Another approach that we often use for hard shadow calculation is the so-called shadow volumes, where we do the basic idea is to treat the shadows as another object. Yeah, question? If an object is not in the shadow, then it is drawn in a regular way. And if it is in the shadow, then you draw it with the shadow color. So you make the color, for example, darker. Or what you could do is you could, and we actually see this in one of the following approaches, we could make the whole scene with ambient light. And then you put the light sources there. And then you calculate which object hits the light. And then you put the color of the light on that object. If it doesn't hit the light, then you don't give an additional color, which means it stays with the global ambient light there. That would be an approach. And that's actually coming in one of the examples here. Good. Yeah, so the shadow maps just decide on a particular pixel, is there a shadow or not, and then you have to consider this in the drawing in a specific way. Good. Yeah, so in the shadow volumes, we look at the shadows as individual objects. So we say we have a light source and we have an occluder, for example, this polygon here, and that creates, then the light source creates a cone, and because of the occluder, we have a part of a cone. So we have this area here that is considered a shadow volume, a volume that is created, or an object that is created by the shadow, and then we use that area to calculate, or we basically check if an object is inside of that volume or not, and if it is inside, first we know that we have to draw it in a shadow, and if it is outside, we know that we don't have to draw it in a shadow. And the difficult thing is, of course, that we can also have overlapping faces, overlapping volumes, and because I think if you remember last time, you should already have an idea about how this is done. This is done again by considering the direction, the positive or the negative subspace. So if we model our volumes in a way that the normal vectors point outside, then we know that if we use the implicit representation, outside it is larger than 0, here it is 0, and inside it is smaller than 0. So we have an easy way to check that. And how we now calculate if a point is inside such a shadow volume or not, that is related to how we usually check if a point is inside a polygon or not, because of course the problem is that we can have overlapping shadow volumes here, and and this is why we do this in a way how we usually do the polygon test, which is if a point is inside a polygon or not. And the test to do this is we place a random point somewhere in our image, for example here, and then we shoot a ray in a random direction. Yeah. So, and then we count how often we cross the polygon. If that number is even, the point is outside of the polygon. Yeah, if it is, and if it is odd, it is inside the polygon. I was just in my head switching even and odd. That was wrong. So yeah, it's easy to see if we have a point here. No matter in which direction we shoot, we will always get an even number of intersections here. And is that correct? Sorry? 1, 2. Ah, yeah. Here. Okay, sorry. Yeah, it's yeah, good. So that should be intuitively clear. There is of course one case where we have to be careful. If we shoot our array in a way that it directly intersects with one of the sides of the polygon, then we have to do a special check to avoid that, or we check it, and if we see it, we just shoot in another direction until we have one where we can count the intersections, and then we can make the decision. Good. And the idea now transferred to the shadow volumes is that if this is our camera here, then if we look at an object, for example this one, if we go to this object, then we see, okay, we intersect here, but since we have overlapping objects, we also intersect here and here. And what we do now, the idea is we basically walk along the ray towards this object, because this is, like if this is our viewing plane, then we have a pixel here that we want to draw, and then we walk along the ray through the eye and that pixel, and then we say now we are crossing a front-facing volume, so we are entering a shadow, so we take a counter and we increase that counter by 1. Then we cross another one, which is again a front facing. So we're entering another shadow volume. So we increase the counter again. And then we are exiting a shadow volume. So we decrease the counter. So don't confuse the plus and minus one with the larger and lower than 0. That's different. That is how we increase and decrease our counter. And then we cross another outside phasing, which means we're leaving another shadow volume, which means we are decreasing the counter again. So our counter in the end is 0. Similar here, where we have the first object where we didn't cross anyone, we also have a 0. But for the objects in the shadow, we always have a counter larger than 0 because we always increase it when we enter a volume and decrease it when we exit it. So if we have a value larger than 0, it always means we have more volumes entered than we exited, which means we are still in at least one shadow volume at this position, which means for these objects we have to draw them in the shadows. There's a question here.
Yes, is there a way to retain these shadow volumes sometimes between frames, or is that not supported by it? If the light doesn't move, you don't move the shadow.
Yeah. That's wait, let me think. Well, if the light does, but if the objects move, then if the scene is still, then of course. But if the objects move, then you have a comment. Then we go to one of the previous slides, one of the special cases that I handled later. Yeah, but good that you already see that. Good. All right. Yeah, so this is basically what I already said. If the counter is then 0, and you can, of course, it's pretty simple that you see that if you have other shadow volumes here, it is basically by the counter you can determine this very easily. And but the problem with this is, of course, it is not very efficient because it is basically we have to shoot rays towards each of the objects, or for each pixel we have to shoot a ray, which is not as inefficient as ray tracing, like it says here, because ray tracing also have the considers iteratively the reflected rays, but nevertheless it is not very efficient. But fortunately there is a hardware support for it, which is called the stencil buffer, and it is kind of related to or very similar to the set buffer, only that it has different supports different operations. First of all, it doesn't store a distance value like the set buffer, but it stores the counter that we have. And it has different operations. The operations is then, of course, modifying this counter by resetting, incrementing, and decrementing it. It also has, the last condition is the conditional drawing of the frame buffer. That is, we draw a pixel if the counter is 0 or not 0, which is then depending on if it is in the shadow or not. And then there is also the conditional resetting and incrementing and decrementing based on a test against the set buffer. That's the operation that is probably not straightforward to understand. But if you look into how it works, then this becomes clear why we need that operation. So what we do is, and this is exactly related to this question that we had earlier between how do we then actually use this information, how do we actually draw it or not draw it. Here we say we initialize the scene by drawing just the ambient light. So basically we draw the scene as everything is in the shadow. Then we compute the shadow volumes, and then we draw the shadow volumes in the stencil buffer. Now draw here is put in quotations because we're not drawing the shadow volumes. We're writing information there where we would draw those objects if we would draw them in a real image. And then we use that stencil buffer information to check if an object is in the shadow or not. And we do this by saying, so we're treating the shadow volumes as objects. And this is, of course, where you see also why this is more efficient, because we're going from a pixel-based to an object-based approach now, where we have this as an object, and then we're drawing the front-facing and the back-facing. Wait, I am confused now. Yeah. Okay. Wait, there was something. I don't know. There is something wrong today with me. Yeah, of course. We we check. We look at an object, and since we calculate the volume phase, we can treat them like objects in our scene. And only we do not draw them, but if their set value is smaller than the objects, that is, if it is in front of it, of the object that is in the set buffer, then we check if it is a front-facing one, we increase the counter. If it is a back-facing one, we decrement the counter. And when we do this with all the faces in front of our object, we have the same value in the counter in the end as if we would walk along the line. So that is the point. So if we draw this here, we increase the counter here and decrease it here. For example, if this is our stencil buffer and we want to draw now the value, we want the value for this point here, then we say the first volume is here. So we increase it here and we decrease it here. And then we draw the second volume, so we increase the counter here and decrease it here. But if we draw, for example, this one, for the first volume, we increase it here, but we do not decrease it here because we know that the set value of the object is lower than the set value of this volume. And this is why we do not decrease it here, and this is why we then end up having the correct counter in here. And this is then why we need this conditional testing against the set buffer. Yeah, sorry, I kind of lost it for a moment. Good, but it is actually a pretty simple test. It's just the interesting idea that we're moving here from the ray-based, pixel-based testing to the volume-based testing. Good. Yes, and then of course we have the scene in ambient light, but we now have in the stencil buffer the information where the light is, so we can redraw the image on those places where we have a light, which is where we have a counter of 0 in the stencil buffer, and all the other positions are ignored because these are the positions in the shadow which we already pre-rendered by using the ambient light. Good. And now we come to the problems of the stencil buffer, one of which you already mentioned, which is that the viewpoint might be inside of the volumes. And then, of course, the calculation of this counter plus and minus is screwed up because we're not entering the shadow volume. And also we can have the problem that the near clipping plane can cut off parts of our volume. And then we have here this situation that when we look towards the object, we don't see the border of the shadow volume. So these are two problems that we have. The first one, we can basically just do a calculation to deal with this a special treatment. We just need to make a clipping here, and then add this to the volume, which is of course something that works, but in practice we have to be careful because it sometimes leads to precision problems because we are drawing an object very near to the clipping plane, which usually is something that is critical in terms of precision. And the second approach that the camera is not within the view frustum within the shadow volume, can actually be solved with a very easy modification of the algorithm. If you think about what we did so far, we looked at the viewpoint and towards the object, and then we increased it when we entered the shadow volume and decreased the counter when we exited the shadow volume. And then we knew at the object how if we entered more shadow volumes than we exited, and that way we knew if it is in the shadow or not. But that works also if we do it on the other side. So this is called a depth pass because we are passing to the depth, and the other is called a depth fail approach, where we go beyond the object, and then again, if we start with a counter initialized with 0, and then increase it every time we enter a shadow volume and decrease it every time we exit a shadow volume, we know that in the end we have to transfer plus and minus then, because of course if we have here +1 and here -1, we get a negative value, and then we know we are inside because we did not, we exited more than we entered. So instead of saying we entered more than we exited, we have to say we exited more than we entered, which is also why we have to check for smaller than 0 instead of larger than 0. But other than that, it is the very same thing. But that way we avoid the situation where the camera is inside of the shadow volume and then leads to a wrong calculation. So that answers your question. But the other thing is still, the other problem still remains, because this problem, of course, we don't have the problem with the near clipping plane, but we have, of course, the problem with the far clipping plane. So if this is our far clipping plane, it cuts off this end of the shadow volume. So we still need to do this special treatment, but at least by switching from a depth pass to a depth fail approach, we have checked, we have solved this this other problem that you were mentioning. Good. So the third approach we're going to talk about is so-called fake shadows, and the name already suggests that this is really a heuristic or a hack, depending, or a trick, depending on how you want to call it. And this idea is basically just to make a couple of simplifications that make the shadow calculation easier, but not as accurate, and but only do it in a way where it might be visual in the image, and try to situations where a little mistake in the shadow calculation might not be as apparent are then avoided, and that's why it's called fake shadows. And the idea is to make 3 simplifications. The first one is that we only consider a few important occluders, only few occluders, important ones of course, which means ones that will create a big or an important shadow. Then only a few important surfaces. So for example, if we have a light here that shines down here, let's assume this bottle is a little larger, then we see here that we have a shadow here, but we also have a small shadow here on the chair. When we can say if that shadow is missing, a lot of people, if they look at the image, they will not realize it, but if they look at the table, they'll see, okay, there is a huge shadow missing there. So this is more important, which is why we say we just model for the table and not for the chair. And the third simplification is that we're projecting not on a complex object, but on a supporting plane, that is the plane defined by that object, which in case of the table is of course the plane that is parallel or defined by its surface. Now and then we can say if we have an occluder and a receiver, we project the occluder onto the receiver in the direction where the light is coming from, and then we draw the shadow here. Now obviously this leads not to a perfect situation. First of all, we are excluding certain shadows like the one here on the chair, and secondly also this calculation can have mistakes. For example, I mean, the first thing is that, like I said, they don't have the same depth. So for example, if we have a chair here like this, and we have a light somewhere here, then we do not only have some shadow here, but we also have that was not intended. Here we go. We also have a little shadow here, so that is excluded. Also, we might have a little shadow here from the glass on the bottle, which is also excluded because they only have the same depth, so we only draw the shadow in that area. But we said we use the whole surface to make the calculation easier, but that would also mean we would draw a shadow here. So it would stick out of the object, and that is certainly not very natural. And the other problem we have with this is that we have double blending. So for example, if we draw the shadow in a way that we just make the color a little darker, then here we also have the shadow from this glass here. So we would make this part here twice as dark, which is of course not what happens in real life, because in real life if you have a shadow, you have a shadow. So it changes at the transition, but not the shadow center itself, no matter how many objects you place in front of it. And this is a nice image illustrating it. So you see here a dinosaur standing on a table, and here the shadow sticks out, and also the parts where you have two parts of the dinosaurs that overlap in the shadow creation. You get a darker shadow in this area here, which is not realistic, but this is what you actually want to have. And to do this, you use again this stencil buffer. So again, a hardware supported approach. We I don't know what happened here. That should be closed. All right. So what we do is, to do this, we use a stencil buffer, and first of all, we reset all the counters. So we have zeros in all our at all pixels representing in the stencil buffer representing this image. Then we draw the scene in a regular way, but whenever we draw a shadow receiver, which for example is the table here, then we increment the corresponding stencil buffer. So here we just have, let's say we just have the table as a shadow receiver. So we increment the stencil buffer when we draw one by 1. So this is larger than 1. Now we're doing the projection of the shadow polygon. So we're projecting this here towards this plane defined by we're projecting, right? If the light is somewhere here, then we're projecting it towards here. So if we're projecting it on the plane, we also get a little shadow here, and this is then this shadow that sticks out here. And then, but now what we do is when we draw it, we look into the stencil buffer. And if we see there is a value of 0 there, then we know that there is no occluder there, although we calculated it because the calculation was based on the surface defined by the occluder, but the image was drawn only, or the stencil buffer was only filled by the actual occluder that we were drawing, the actual part of the table. So we know that this is 0, and that means we do not draw the shadow. We calculate the shadow for the plane, but only draw it when we actually know that there is an object there, and we know that because we filled the stencil buffer while we were drawing it. The other thing we have to do when we are drawing it, when we draw a shadow there, we decrease the stencil buffer again, so we get a value of 0 again as soon as we have drawn a shadow. So if we have drawn the shadow of the bottle here, the parts where we have a shadow now, which is probably here, are also set to 0. So the stencil buffer now contains only these parts here larger than 0. And this here is again is 0. And that way we can avoid this double blending problem that we have here. Because if we draw now, do the projection of the second object, and we draw it here, then we see in this area here the stencil buffer is larger than 0, so we have to add this shadow here. But here we see the stencil buffer is already 0, so that is then treated as if there is no occluder, which means we do not draw the shadow, which means we do not draw a second shadow over it, which means that we end up with a correct image like here on the right side. Good. All right, so these are the three major approaches for hard shadows that we want to discuss. And like I said, the first one also, I think, or I hope that a lot of you will implement. Now, just one word on the soft shadows, because like I said, soft shadows are very expensive, which is why they're often not done, or the approaches to do them are much more complicated, which is why we'll not go into them, but just to say the basic idea about how it usually works. It usually works that you just take a couple of light sources that you're modeling. So instead of having a single light source, you model several ones, and then you do a blending of the color values in that area here, because that, of course, you see then is depending on how many light rays hit your object here, and that way you get this smoother transition at the borders than you get here. Good. So this is all that I wanted to talk about, that I want to tell you about shadows. Like I said, I will put some references online in case you want to have more information, because this is not covered in the book. There is a little bit information about this in the book, but it's not really, it's either different than I did it, or it's very, very limited. Yeah, so like I said, I will put references online, but for the exam, what you get in the tutorial and what I told you today in the lecture should be sufficient. Are there any questions? No? Then we're done for today, and see you again Thursday.